Good morning, everyone. Today's presentation is a continuation from chemical bonding, part 1. In this session, we will focus on ionic and covalent bonding, delve into the concept of intermolecular forces, and explore the molecule shape and the various types of intermolecular forces and their implications. Let's get started. But before we dive in, if you are new to this channel, hit the subscribe button. I personally welcome you to this Jom Studylah channel, and let's get started. Ionic, electrovalent, and covalent bonding. Electrovalent bonds, also called ionic bonds, are formed between atoms that transfer electrons from one to the other. This bond don't have a specific direction because the atoms are simply held together by the electrostatic attractions between the positive and negative charges. The bond is non-directional and can be formed in any direction as long as the charges attract each other. On the other hand, covalent bonds are formed when atoms share electrons, and these bonds are directional, meaning the atoms arrange themselves in a specific way to minimize the repulsions between electron pairs around the central atom. And this leads to distinctive shape depending on how many pairs of electrons are shared. Electrovalent bonding, covalent bonding, and molecular shape is primarily about how atoms bond are arranged themselves and how the number of electron pairs 2, 3, and 4 affects the shape. For electrovalent ionic bond, ionic compounds do not form simple molecules with distinct shape like covalent compounds. Instead, they form a giant lattice structure where ions positively and negatively charged are arranged in a repeating pattern. So, ionic bonds don't have a molecular shape in the same sense as covalent bond. For covalent bonding and molecular shape, when atoms form covalent bond, they share electrons. The number of electron pairs around a central atom influences the shape of the molecule. Refer to the next slide on how it works for 2, 3, and 4 electron pairs. Simple molecular shape. When atoms form covalent bonds, the electron pairs around the central atom repel each other. The number of electron pairs determine the electron geometry and molecular geometry. For 2 electron pairs, example carbon dioxide, the atoms are arranged themselves in a linear shape, 180-degree bond angle, and in a molecule like carbon dioxide, there are 2 bond pairs of electrons around the central atom carbon, and the electrons spread out to be as far apart as possible, giving a straight line shape. Second electron pairs, example is a boron trifluoride. The atoms arrange themselves in a trigonal planar shape, 120-degree bond angle. As shown in this slide, with 3 bonding pairs, the molecule arranges itself in a flat triangle with 120-degree bond angles between the atoms. And for 4 electron pairs, example methane, the atoms arrange themselves in a tetrahedral shape, 109.5-degree bond angle. Let's look into the bond energies, bond length, and bond polarities. Bond energy is the amount of energy needed to break a bond between 2 atoms. Key point, the higher the bond energy, the stronger the bond. Stronger bonds require more energy to break. Shorter bonds tend to have higher bond energy because atoms are closer together, making the bond stronger. Bond length is the average distance between the nuclei of 2 bonded atoms. Key point, shorter bonds are usually stronger because the atoms are closer. For example, a triple bond is shorter and shorter than a single bond. For multiple bonds, which is double, triple, they are shorter than single bond because the atoms are pulled closer together. Bond polarity is the distribution of electrical charge across a bond due to differences in electronegativity between the atoms. Key point, if two atoms have a significant difference in electronegativity, the bond is polar, meaning one atom pulls more on the shared electrons, creating a dipole positive and negative ends. If the electronegativity difference is large, like in HCl, the bond is more polar. If it is small or zero, like in H to H, the bond is non-polar. Intermolecular forces. These are forces that act between molecules, affecting their properties like boiling and melting point. The first intermolecular forces is van der Waals forces. So for London dispersion forces is the weakest type of intermolecular force. It happens when temporary fluctuations in electron density create tiny, short-lived dipole in molecule, which then attract each other. Key points, it found in all molecules, but especially important in non-polar molecules, like noble gases, or diatomic molecules like oxygen. Example for London dispersion forces or van der Waals forces is the attractions between two oxygen molecules. The second intermolecular forces is a permanent dipole-dipole interactions, which occur in molecules that have a permanent dipole due to differences in electronegativity between atoms like HCl. Key points, molecules with permanent dipole attract each other opposite charges, and these interactions are stronger than van der Waals forces. Example for permanent dipole-dipole interactions is the attractions between HCl molecule, where the positive H side of one molecule attract the negative Cl side of another. And the third example of intermolecular forces is hydrogen bond. Is a special type of dipole-dipole interaction, and it happens when a hydrogen atom is bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine, creating a strong dipole. Key point, hydrogen bonds are stronger than regular dipole-dipole interactions, but still weaker than covalent bonds. Example for hydrogen bonds is the attractions between water molecule, H2O, where the hydrogen of one molecule is attracted to the oxygen of another. Differences in strength cause of intermolecular forces. Strength for hydrogen bonds, they are the strongest. Permanent dipole interactions are weaker. And for van der Waals forces, van der Waals forces, the strengths are the weakest and cause. Van der Waals cause temporary dipoles, dipole-dipole cause permanent dipole, hydrogen bond cause special dipole-dipole involving hydrogen, and electronegative atoms like oxygen, nitrogen, or fluorine. Van der Waals is the weakest temporary dipole in all molecules. Dipole-dipole is a stronger permanent dipoles in polar molecules, and hydrogen bonds is the strongest special dipoles with hydrogen and highly electronegative atoms. This is the questions. Example for intermolecular forces. And for the list of material given for methanol, magnesium, iodine chloride, argon, and aluminium. The question is, for each of the material in the list below, predict the main types of intermolecular forces that exist in the material like methanol, magnesium oxide, iodine chloride, argon, and aluminium. For methanol, intermolecular forces is hydrogen bonding, dipole-dipole, and London dispersion forces. The reason being is methanol can form hydrogen bond because of of its OH group, and it also has a polar nature, dipole-dipole, and weak forces between molecules. For the magnesium oxide, the intermolecular force is ionic bond. Reason being, magnesium oxide is made of positive and negative ion, which is Mg2 positive and O2 negative, that are strongly attracted to each other. For iodine chloride, intermolecular force is a dipole-dipole and London dispersion forces. The reason being is iodine chloride is polar, so it has dipole-dipole attractions plus weak London dispersion forces. Argon intermolecular forces is a London dispersion forces. Reason being is argon is a noble gas, so the only force between atom is the weak London dispersion forces. And aluminium, the intermolecular forces is a metallic bonding. And the reason being, aluminium atoms are held together by a metallic bond where electrons move freely throughout the metal. Metals have unique properties because their atoms are arranged in a regular pattern, similar to how ions are arranged in ionic crystal. However, unlike ionic crystal, all the atoms in the metals are the same, and their outer electrons are not tightly bound to any one atom. Instead, these electrons move freely throughout the entire metal structure. This sea of delocalized electrons is what gives metal their characteristic properties such as electrical conductivity and malleability. In conclusion, we have explored the fundamental concept of ionic and covalent bonding, along with the various intermolecular forces that play a crucial role in determining the properties of the substance. Understanding this focus helps us to delve deeper into how molecules interact and behave in different environments. And I hope this session has provided clarity on the topics and its application. Thank you for your time. And don't forget to like, share, and subscribe to Jom Study Live YouTube channel for more educational content. See you in the next video.